In March 1984, Airbus formally launched the A32O program. The aircraft the company described would be the first commercial airliner in the world to use full-authority digital fly-by-wire flight controls. Controls in which the pilot's inputs would be converted to electrical signals, sent to computers, and then translated into commands to the aircraft's surfaces, with the computers having authority at the edge of the flight envelope to refuse or modify those commands if executing them would push the aircraft past its certified structural or aerodynamic limits. The development budget was approximately $2.5 billion. Not a single airline had yet committed to the type. The aviation establishment's response was cautious at best and hostile in places. Pilots' associations raised concerns about automation reducing crew authority. Several regulatory bodies were uncertain how to apply certification standards written for mechanically connected controls to a system where the physical connection between pilot and control surface no longer existed. Boeing, Douglas, and Lockheed had all built aircraft with elements of computer-augmented flight control, but none had committed to a system in which the computers held final authority over the aircraft's structural limits. Airbus had designed that authority into the A32O from the first sketch. In a conventionally controlled aircraft, every commercial jet from the Comet through the 747, the pilot's control column is connected to the aircraft's control surfaces through a combination of cables, push rods, and hydraulic servos. When the pilot pulls the column back, a cable runs through the fuselage to a hydraulic actuator at the tail, which moves the elevator, which raises the aircraft's nose. The connection is mechanical. The aircraft does what the pilot commands. If the pilot pulls hard enough and fast enough, the aircraft will do exactly what the pilot commands, even if what the pilot commands will kill them both. This is not a hypothetical. In-flight structural failures caused by pilot-induced overloads, pulling an aircraft through a load that exceeds its certified structural limits, have killed crews and passengers throughout aviation history. A pilot encountering severe turbulence and instinctively hauling back on the controls can impose loads that pull the wings off an otherwise airworthy aircraft. A first officer making aggressive rudder inputs during a wake turbulence encounter can separate the vertical stabilizer from the fuselage. In a conventional aircraft, there is nothing between a pilot's intent and the aircraft's structure except the pilot's own knowledge, discipline, and speed of judgment. The conventional system had one genuine advantage: feel. The mechanical connection between control column and surface meant the pilot could sense, through resistance in the controls, how hard the aircraft was working. Heavy aerodynamic loads on the surfaces translated into physical pressure back through the column. An experienced pilot could feel when the aircraft was approaching its limits, without reference to any instrument, through the resistance in their hands. The weight of the mechanical system was substantial. On a 747, the cable runs, pulleys, hydraulic lines, and actuators for the primary flight controls add thousands of pounds to the airframe's empty weight. Electrical wires carrying a signal weigh almost nothing by comparison. The system Airbus developed for the A32O replaced the mechanical runs with 7 flight control computers, 2 handling elevator and aileron commands, 3 handling spoilers and elevators in backup, 2 providing flight augmentation. These computers ran dissimilar software written by independent teams in different programming languages and used different hardware processors, specifically to prevent a single software or hardware error from disabling the entire system simultaneously. They cross-checked each other's outputs continuously. If one computer produced a divergent result, the others could identify and isolate it. The pilot's sidestick, a small joystick mounted on the side console rather than the traditional column in the center, sent the computers a statement of intent rather than a mechanical command. When the pilot pushed the sidestick forward, the signal that reached the computers was something close to, "I want to pitch down," not "move the elevator down this specific amount." The computers translated the intent into the specific surface movements required to achieve the desired pitch rate, accounting simultaneously for airspeed, altitude, aircraft weight, and the outputs of the sensors monitoring the aircraft's attitude. The A32O could be flown precisely in any condition, not because the controls were connected to the surfaces, but because the computers were good at interpreting what the pilot wanted and implementing it efficiently. What the system also did, and what made it fundamentally different from anything before it in commercial aviation, was define a set of limits the computers would not cross regardless of pilot input. An A32O pilot pulling full aft on the sidestick will not stall the aircraft. The computers monitor the wing's angle of attack continuously. As the angle approaches the threshold at which the wing would lose its lift, the computers hold the aircraft at the maximum safe angle of attack regardless of how far the sidestick is pulled. The pilot's demand is accepted up to the limit and no further. A pilot commanding more than 67 degrees of bank will find the computers working against the input. The aircraft will not go to 90 degrees regardless of sidestick position. A pilot diving past the maximum operating speed will find the computers applying pitch-up inputs and drag before the limit is reached. A pilot attempting to impose a load factor above 2.5 G in clean configuration will find the input refused before the structure approaches its design limit. These protections are not theoretically interesting. They are the specific category of accident: pilot-induced structural failure, inadvertent stall at low altitude, gross attitude departure, that the A32O's protection laws were designed to prevent. Each one addresses an event type that had killed crews in conventionally controlled aircraft, and that the A32O's architecture made aerodynamically impossible in normal operation. By the way, if you're into stories like this, subscribing takes 2 seconds and there's a lot more coming. On the 26th of June, 1988, the A32O had been in commercial revenue service for 68 days. Air France was conducting a demonstration flight at the Mulhouse-Habsheim Airshow in Alsace. The aircraft, registration F-GFKC, a brand new Air France A320, was flown by Captain Michel Asseline, one of Air France's most experienced Airbus pilots, and First Officer Pierre Mazière. The planned maneuver was a low-level, low-speed fly-past over the runway at a minimum announced altitude of 100 feet, followed by a go-around with full thrust. The fly-past was specifically intended to demonstrate the A32O's low-speed handling characteristics and the visibility from the cockpit. The aircraft crossed the runway threshold at approximately 30 feet above ground level, a third of the announced minimum altitude. Its speed was near the lower edge of the protected envelope, close to the angle of attack at which the protection laws would activate. As the aircraft reached the far end of the runway, and the pilots applied full thrust, the CFM56 engines began spooling up from their low thrust setting. The spool-up time for those engines, the time between the thrust command and the delivery of full power, was between 5 and 8 seconds. At 30 feet altitude, at that speed, crossing into a forest at the runway's end, the aircraft did not have 5 to 8 seconds. The trees hit the aircraft's belly and right engine. The aircraft came down into the forest. Of the 136 people aboard, 3 died, all passengers who had been unable to evacuate quickly enough before fire spread. The aircraft was destroyed. The investigation by the French Bureau d'Enquête et d'Analyse established the cause with specificity. The aircraft had been flown below its announced minimum altitude. The full thrust application had been late. The engines, operating correctly, required spool-up time that the altitude margin did not allow. The fly-by-wire system had functioned exactly as designed. Alpha protection had activated and held the aircraft at maximum angle of attack, preventing a stall. What it could not perform was the function of ensuring adequate altitude for a go-around, because that function had never been part of its design. Captain Asseline publicly disputed the findings, alleging that the computers had failed to respond correctly to his thrust inputs and claiming the flight recorder data may have been altered. French courts examined those claims and rejected them. Asseline was convicted of involuntary manslaughter. The crash entered public memory as evidence that the A32O's computers had somehow failed. The opposite was true. The computers had done everything they were designed to do. What the protection system could not prevent was an approach to a forest at 30 feet of altitude, an outcome that had nothing to do with stall, structural failure, or any of the accident categories the protection laws addressed. Boeing flew its 777, the first wide-body aircraft with full digital fly-by-wire controls, in June 1994. Its system differed from the A32 O's in one specific way that reflected Boeing's assessment of what the aviation community would accept. The 777's protection laws were less restrictive. A 777 pilot can, with sufficient force and persistence, push the aircraft outside its certified envelope. The computers provide strong resistance and clear warnings, but they do not hold an absolute limit. Boeing's position was that final authority must remain with the pilot in all circumstances. Airbus's position, embedded in every subsequent aircraft it built, the A330, A340, A350, A380, was the opposite, that the envelope protection should be genuinely hard, and that the weight of evidence supported this approach because the category of accidents the protection prevented, inadvertent structural failure, stall at low altitude, was killing far more people than the category of accidents that could theoretically result from a computer refusing a correct instruction in an unusual situation. The 30-year record since the A32O entered service has been informative. The A32O family, which has grown to include the A319, A321, and their new engine variants, has delivered more than 8,000 aircraft and accumulated one of the lowest fatal accident rates in commercial aviation history. The accidents that have occurred have involved, in the documented cases, factors including deliberate action by a pilot, crew failure to manage aircraft state, and mode confusion during automation transitions, none of which were among the categories the fly-by-wire protection system was designed to prevent, and all of which would have been equally possible in a conventionally controlled aircraft. Bernard Ziegler, the man who most directly shaped the A32O's fly-by-wire architecture, gave an interview some years after the aircraft entered service in which he described the protection laws not as restrictions on pilots, but as a definition of the space within which pilots were entirely free. The aircraft would do anything the pilot commanded within the certified flight envelope. It would simply not go outside that envelope regardless of what was commanded. Ziegler's analogy was of a surgeon who operates with precision instruments that will not cut deeper than a certain point regardless of how hard the surgeon presses. Not a limitation on the surgeon's skill, but a safeguard allowing the surgeon to operate with confidence at the edge of what is possible without fear of catastrophic error. The aviation establishment that had been skeptical of the A32O in 1984 accepted the design principle by the 1990s, and every major manufacturer of large commercial aircraft now builds fly-by-wire systems into their new designs. The specific form of those systems, how hard the limits are, whether the yoke is replaced by a sidestick, how much authority the computers hold in extremis, remains a subject of legitimate engineering debate. What is not subject to debate is that the A32O proved the concept viable, commercially successful, and by the available evidence, safer than the mechanically linked alternative it replaced. The aircraft the industry doubted in 1984, and the press condemned in 1988, will almost certainly carry more passengers in 2040 than any other aircraft type in history. If the story was worth your time, hit like and subscribe, and drop what you think in the comments.